Hi everyone, this is going to be a quick tutorial on how to use your DNA ladder or standard to estimate the sizes of your fragments of DNA. So first, I just want to review the DNA ladder or standard or marker that we use whenever we run an Agarose gel. It's a DNA solution composed of many fragments of DNA with different known lengths. So it's a set of pieces of DNA and we know their sizes. And why we have a ladder, we have it as a reference to estimate the sizes of our unknown fragments. Here are some examples of ladders or standards from different companies. But usually when you buy a ladder, like we said, it comes with a little map showing you what the pattern of bands you would expect as after you run it on a gel, and then it also indicates the sizes of the different bands since we know what sizes they are. And there are many different types of ladders, and again how they're different is what sized bands do they have to use as a reference to estimate the sizes of your DNA bands. And so effectively, in order to estimate the sizes of your unknowns or of your pieces of DNA that you're running out on the gel, you want to create a standard curve from your DNA ladder. And we're going to be comparing the sizes of the fragments with how far they migrated down the gel. And I'm going to show you how to do that in the next couple slides. Once we do that, what we're basically going to do is we're going to establish a relationship between fragment size and distance migrated using our standard fragments. Once we do that, we can then use that the line that establishes that relationship on the graph to then estimate our unknowns. So let me show you how we do that. So by now all of you should have a picture of your gel, and I'm just going to use this hypothetical gel right here as an example. In this gel, the standard was loaded in this lane right here, so this corresponds to the standard, the DNA standard lane. What you're going to want to do first is, if your picture is very small of your gel, it might be easier to print out a picture of your gel that's been expanded in size, so you make it a little bit bigger on your piece of paper. So you want to get a picture of your gel and print it out, and then what you're going to do is you're going to take a ruler and you're going to set up the ruler so that the zero line of the ruler is right lined up with the well of the gel, the wells, okay? And then what you're going to do is you're now going to measure how far each piece of DNA migrated down the gel. So for example, this first DNA fragment migrated, let's say that this is in centimeters, it migrated 10 centimeters from the well. And let's say that according to our map, that band is 11,000 base pairs long. You do this for the rest of the bands, and what you're going to generate are two numbers for each DNA band. You're going to generate, you have the size of the band, right, in base pairs, and then you have the distance it migrated from the well. From there, you generate a table with these two bits of information, so the size of the DNA fragment of the ladder or the standard, and then the distance traveled from the well. If you were to plot this data on a graph where on the x-axis you have distance traveled, usually it's in centimeters or millimeters, and then on the y-axis you have fragment size, you would get something like this. You would see that the relationship between the two is actually not linear, it's logarithmic. So we don't get a straight line from that relationship. I also want to point out that it is a negative relationship. So the longer the fragment travels down the gel, the smaller that fragment is, which makes sense, right? It travels faster if it's smaller. So it's a negative logarithmic relationship. Now the fact that it is a logarithmic relationship makes it difficult for the type of analysis we want to do. We wanted to use this data to determine our unknown fragment sizes. So it's preferable to have a linear relationship. We can still take this data and convert it into a linear relationship. And what we would have to do in order to to make that change is instead of plotting this data on regular graph paper, we have to plot it on what we called semi-log graph paper. Here is semi-log graph paper, and what it is on one axis, and on this case it's the x-axis, you have regular graph paper or regular intervals that you would normally see on graph paper, and on the y-axis it's actually the logarithmic scale. And so on the y-axis is where we would plot base pairs, and so you're really plotting the log of the base pair size. So if we were to take the same data from our table, by using this type of graph paper, instead of getting a curve, which indicates the logarithmic relationship, you would get a linear relationship. You would get a line, or a trend line that you could make from your data. So this is the graph paper that you need to use. If you want to do it by hand, I will post a copy of the semi-log graph paper. Those of you who are very savvy on Excel, you can actually fix it so that Excel would do semi-log graph. And just a little pointers on how to set up the y-axis here. So if you look, it's in tens. So 1, 2, 3, 4, 5, and all the way 9, and then 10, and then, or 1, 2. So you can see that it's in tens, right? The first set of 10, each tick mark represents 100 base pairs. So this one would be 100 base pairs, 200, 300, 400, 500, all the way then up to 1,000. And then the next set of 10, each interval represents 1,000 base pairs. So this is 1,000 right here. This would be 2,000, 3,000, 4,000, 5,000, all the way up to 10,000. And then the next set of 10, the intervals then are divided by 10,000 of base pairs. So this is 10,000, this would be 20,000, 30,000, 40,000, etc. So you could go all the way up to 100,000. Now our fragments are definitely within, are small. They're within the range that, that this would provide, from 100 to 10,000. On the x-axis, it really depends on if you're using centimeters, millimeters. Just make sure that you use your whole space so that your graph is not really tiny. Use up the whole paper so that you get a nice big amount of room to plot your data. Once you've plotted your standard fragments and gotten a linear relationship between the size of the DNA, at least the log of the size of the DNA, and the distance migrated, you can then measure your unknowns, how far they migrated down the gel. So this is your gel here. And we usually run the standard in the first lane, so you would make your standard curve based on these fragments. Then for your other samples, to estimate the sizes of your PCR bands, you're going to take your ruler, measure how far down the bands migrated. Let's say we got 4.5 centimeters. Then you would go to your graph and you would say, well, my band migrated 4.5 centimeters. That corresponds to around, like 750 base pairs. And so I estimate that my fragment is 750 base pairs long. So you're going to use this graph to estimate your unknowns. It's very much like the protein quantification lab. So what I'm going to collect from you is both the table of your sizes and distance migrated, and this graph here.